Hey friends, welcome back. In this video, we are going to talk about what a gradient is, as well as how do we calculate a gradient. So a gradient is just a far more efficient formula for the directional derivative for a differential function of f. So in order for us to define this, let's start with a parametrized line. So we're going to start with the line x equals x naught plus s times s sub, or u sub 1, and y equals y naught plus s times u sub 2. And this passes through, if I can spell, through some point p naught located at x naught, y naught. So these are parametrizing the arc length parameter s, increasing in the direction of the unit vector u. So we could rephrase this and say the derivative of f with respect to s in the direction of u at point p naught is the partial of f with respect to x at p naught times the derivative of x with respect to s plus partial of f with respect to y at p naught times the derivative of y with respect to s. And so this can be defined using the chain rule. If I look at differentiating both of these parametrized pieces with respect to s, so dds of x equals x naught plus s times u sub 1, and dds of y, which equals y naught plus s times u sub 2, we would determine that ds is equal to u sub 1, and ds is equal to u sub 2. So that allows me to take my formula up above and simplify it. We've got the partial of f with respect to x at p naught. Ds is equal to u sub 1 plus the partial of f with respect to y at p naught, and the derivative of y with respect to s is u sub 2. Now, if we take this, and again, this is the directional derivative. If we take this here, and we think about this as being a dot product, and we say, well, what were the two vectors that existed before we dotted those values? So reversing that dot product, we end up with partial of f with respect to x, p naught, vector I, plus partial of f with respect to y at p naught. We got vector j, and that would be dotted with u sub 1i plus u sub 2j. So what we have here is representative of the gradient at p naught, and this is saying in the direction of u. So this says the derivative of a differentiable function f in the direction of u at p naught is this special vector representing the gradient dotted with u. So let's present the definition for gradient. So here we have our definition, and I'll actually leave that last step up there for the directional derivative, because you see this that we just calculated showing up down here. So the gradient vector, or rather just the gradient of this multivariable function, is the vector, and we can say this is, we can read it as gradient of f, del f, grad f. So the gradient vector is represented by the partial of f with respect to x times the vector I plus partial of f with respect to y times the vector j. The value of the gradient vector is obtained by evaluating the partial derivatives, these two partial derivatives at that point. And so if we are considering it at a specific point, this is just a general gradient for anywhere on the function, but if we wanted to evaluate it at a specific point, P naught, we would throw that notation in there. So we could say del F at P naught or del F at this ordered pair X naught, Y naught. All right, so this upside down delta, in math, we read that as a del symbol, but you can also say gradient or grad. And so what this is telling us, remember what we calculated up here. We said the directional derivative of f with respect to s in the direction of u at p naught. This was my directional derivative, and the directional derivative was a dot product of this gradient vector times the direction unit vector u. So we can restate the directional derivative as a dot product. We have a new theorem, and that's right here. And this just says that the directional derivative is a dot product. So now that we understand what a gradient is, if we have a multivariable function which is differentiable in some region R containing a point P naught, then that directional derivative, so the derivative in the direction of u at the point, is equal to the gradient evaluated at the point dotted with the u, the unit vector giving us the direction. So the dot product is the gradient of f at p with the vector u. In brief, we can just say the directional derivative, the derivative in the direction of u of the function, is equal to the gradient of f dotted with u. So now let's do an example. For this example, we're going to find the derivative of the function at a given point, or p naught, in the direction of this v vector. So my multivariable function, f of xy, is x times e to the y plus cosine of x times y. So we need a couple of things. We need to know our unit vector. So we're going to have to find the magnitude of this and divide by the magnitude. And then for the gradient, we need the partials of f evaluated at the point with respect to x and then also respect to y. And once we have those, we can do our calculations. So my first step will be to find that unit vector. And the magnitude of v is the square root of 3 squared plus technically negative 4 squared, which is the square root of 25, which gives me 5. So my u vector is going to be v divided by its magnitude, which is 3I minus 4j divided by 5. So my unit vector is 3/5 I minus 4/5 j. All right, so I know what u is. I need to find the gradient so I can dot product it with this u to find the directional derivative. So now I'm going to need the partials of both, or the partial of f, both with respect to x and y, and we'll evaluate that. So we're going to find the partial of f with respect to x at that ordered pair 2, 0. So partial with respect to x, that means e to the y is a constant or a coefficient. So I have e to the y. Technically, we have a plus, but the derivative of cosine is negative sine. So that's going to be negative sine of xy. I'm not done taking the derivative because I have to use the chain rule here. So the derivative of the inside is just going to be, we've got a times y. So I prefer to have that y at the front. So I'm going to say minus y sine of x y. And we need to evaluate that at the ordered pair 2, 0. So that is e to the 0 minus 0 times the sine of 0 times 2. which e to the 0 is just 1. All right, so we'll do similar partial with respect to y at that ordered pair of my multivariable function. So x is a coefficient. The derivative of e to the y is e to the y. So I will have x e to the y. Taking the derivative of cosine, I'm going to get negative sine of xy, x times y. And I need to take the derivative of the inside. So x is a coefficient. I end up with an x here in front. So now we need to evaluate that at the ordered pair, which is 2 times e to the 0 minus 2 times the sine of 2 times 0. Sine of 0 is 0, so 2 times 0, all of that goes away, and we end up with 2 times e to the 0, or 2 times 1, which is 2. So now that I know those two pieces, I know my gradient of f. So recall the definition we just stated. The gradient of f, or del f, is going to be that partial of f with respect to x times my vector I plus partial of f with respect to y, again evaluated at that point, with respect to j. So gradient of f is going to be 1i plus 2j. Therefore, my directional derivative, the derivative in the direction of u of this function evaluated at 2, 0, is going to be del f evaluated at 2, 0, dotted with u. So we know what that del f is. We just found that. That is I plus 2j. And we're going to dot that with u. Recall we found u up here, 3/5 I minus 4/5 j. So we've got 3/5 I minus 4/5 j. And that dot product is just going to be 1 times 3/5 plus 2 times negative 4/5, or 3/5 minus 8/5, which is negative 5/5, which is negative 1. Now, let me pull a picture in that kind of explains visually or helps you visualize what we're doing. So what we have here is our surface, and we're thinking about these level curves as representing the surface of that multivariable function, the number of level curves of f. So if we picture the gradient of f as a vector within the domain, what we see is the rate at which my function changes at this point, the rate at which my function changes, considering in that direction of u, is the gradient of f dotted with u, which is negative 1.